Hi, United, it's Mr. Carson here. Thermal energy and heat, specific heat capacity. You've started this and you did the experiment. By now you've done it with the metal blocks. And we're going to quickly review some of that and then look at how we can use this specific heat capacity. I know there's a little bit you've started with, so we're going to push on. The whole problem is with measuring energy is finding where it is and getting an exact measurement of the energy itself as it moves. So what we do is we look at how it impacts on the surroundings. Now you've already seen with me in the previous lesson how energy moves from where there's a lot of it to where there's less of it. It always moves from, so for example, heat moves from hot to cold, and this explains why our hot coffee, if we leave it out, becomes cold, or why our cold drink, if we leave it out, becomes warmer. So if we can think about what's going on, and we know this energy transfer occurs, then surely we could look at what happens to what's around the particular thing. And the best way to do that is to look at the energy changes, because we have some other interesting information provided. Each type of matter that we're talking about that could be the surrounding will act differently, because all of them have what's called a specific heat capacity. And this basically tells us how much energy we need to put into something to get it to increase in temperature. So obviously the lower the value, the better the conductor of heat. So it would let heat move in and let heat move out very, very quickly. Now this is based upon the idea that all matter contains atoms. So in gold there's gold atoms, aluminium there's aluminium atoms. So each of them will act differently to the way heat moves through them. And so each of them will have a value, and that comes later on. So here in essence is what we're trying to do with this whole idea of calorimetry. And calorimetry is basically looking at measuring changes in the surroundings to deduce how much energy was in something, or how much energy, more importantly, moved out or moved into something. So if we look at the first one here with the coffee, we can actually see that what's going on is heat is moving out to the air, and if we could measure the temperature of the air, then we could work out how much energy, heat energy, came out of the coffee. Now the one big problem of course with that is because the air is so huge. So the effect on small amounts of the air would be very, very little, because there's so much of it to transfer that heat to. And this is the opposite if we have this coming in. Now some of us might have heard this word before in terms of heat energy. Your teacher last year might have talked about if heat is moving out, we say it's exiting, or this is an exothermic process. And if heat is moving in, you might have heard that it's going into, so it's an endothermic process. So now let's get down to specifics. We've seen if we want to measure, we can do these things. So let's have a look at this equation. And it's a very, very useful equation for lots of reasons. Q is the energy that is either moving in or moving out. All right? We are going to be doing a lot of hours, and people like using water as the surrounding. So we actually put things in the middle of water and let the energy move into it. This is a thing called a bomb calorimeter, and you actually surround your test material with water and measure the temperature of the water to see how much energy is transferred. Now, but we've got to be very, very careful with our units. The energy that's transferred is measured in joules. The mass of the water, the surroundings of our material, in the case of the metal blocks, is water. So we have to talk about the mass of water that's there. Now, luckily for us, 1 gram of water 1 gram of water has a density of 1 gram of water is equal to 1 cm cubed of water, because this is due to the density is 1 gram per cm cubed. All right, so that means every cm cubed of water has a mass of 1 gram. So every litre, which is 1,000 cm cubes, has a mass of 1,000 grams or 1 kilogram. The specific heat capacity is measured in joules per kilogram per degree C, and the temperature change must be measured in degrees C. Now, if we've got all these conditions met, then this equation comes to suit us down. So let's have a look at this one we've got now. We've got a situation that occurs in labs quite often where a student adds a chemical to a fixed volume of water and we see what goes on. Now, we use a styrofoam cup to try to limit the amount of heat that is lost to the air outside. Styrofoam is a reasonably good insulator of heat, so that's good. So let's start filling in what we've got, and then we can work it out. Right, we are trying to find the energy, so Q we don't know. The mass of water is 50. Now remember that every cm cubed has a mass of 1 gram, so that'll be 50 grams. But to use the equation, this has to be converted to kilos, which is 0.05 kg. Our temperature is temperature change. We start up at 23 and go to 31. So temperature change, so delta, we should put delta in front of there, is 31 minus 23, which is 8 degrees C. So we've met all the requirements for our equation. We've got the mass in kilos, we've got C expressed in joules per kilogram per degree Celsius, and we've got the temperature change in degrees Celsius. So I'd like you to try to work through this, and I will give you the answer in a moment. So all you have to do is plug in the thing. So our equation is Q equals M times C times delta T. So we'll start plugging those things in. Now, hopefully you have got the correct answer, and hopefully you have been shown this on the Edpuzzle. Let's have a look now. Let's go through. For those who have not quite managed, let's have a look at what this is. So let's plug the numbers in. So 0.05 times 4186 times 8, and we should end up with a number of 1674.5 joules, and probably it looks better if we make that into a bit more of a better number by making it into kilojoules. So it's 1.67 kilojoules of energy is transferred. So hopefully we're right with that one. So you just simply have to plug in numbers. But we can look at instances in the coming questions which talk about what happens if we change. So let's move on to question number 2. As you can see in this case, we are going to burn some fuel and heat some water in a container, and we want to work out what the temperature is. So let's look at what we know and we can work from there. So it says here in the question, and I'll put it in red to help us, that we have 2 grams of fuel. And if we're going to burn both grams, we see that it's 2 times 25 kilojoules, which is equal to 50 kilojoules of energy. But our equation requires it to be in joules, which is 50,000 joules. Right, the mass of the water is 50 grams again, which is equal to 0.05 kilograms. Our C is still the same, water doesn't change, so it's 4186 joules per kilogram per degree C. And finally, our delta T. Now, if we go to delta T, we know that our starting temperature is 23. And we're trying to work out how much goes above it. So let's put the equation in. So if Q is equal to M times C times delta T, then delta T is going to be equal to Q divided by M times C. Right, let's stop there, and I want you to plug the numbers in and go through and answer the question. All right, and I'll see you in a minute with the answer. All right, hopefully you were able to do this successfully, but if you had problems, let's go through it together. All we do is we plug in some numbers. Now we see that Q is 50,000, or if you like, 5 times 10 to the 4. Now, scientific notation is very, very helpful sometimes, and if you have a proper calculator, that would be the same thing. Now, then we've got divided by M times C. Now, our M is 0.05 times C is 4186. So if we then do those sums, we should end up with a number that looks something like this. Right? But that's only half of it. We've worked out what the change is, so now final T is 23 plus the change, or delta T, and so that would give us 261.9 degrees C. Quite warm, as you can see, for 2 grams of fuel. So a lot of energy comes out of fuel at the time. All right, let's just do one more example in example number 3. Let's go to it now. All right, in example 3, very similar, except we're going to change it again. And this time we're looking at the mass of water that we don't know. So let's start plugging in some numbers we do know. Really good idea, I know you've been practicing this. So it's 2 times 20 for our Q, and that's in kilojoules. So that's 40 kilojoules, or 40,000 joules. And we could always say that could be correspond as 4.0 times 10 to the 4 joules. Excuse me. Right, our mass we don't know. So we're going to try to find that out. C is still, because we're still using water as our surrounding, 4186. And we have the temperature change is going to be, excuse me, 41.5 minus 23, which is 18.5 degrees Celsius. Sorry about my handwriting. So let's put this again. So if Q equals M times C times delta T, then this time M is going to be Q over C times delta T. All right, how about you have a go at plugging in some numbers, answer the question, and then I will go through the answer with you after this. All right, hopefully you got that right, but for those who had trouble, let's look at it. We've got up to this stage, and we know that we can start putting in numbers. So we've got 40,000 divided by 4186 times 18.5. And we should end up with a number that looks like this. But that is in kilos, or litres if you like. So if it's in litres, we don't like it too much. So how about we convert it to a steady form? So the volume is going to be equal to 0.52 litres, or as we'll learn later, dm cubes. And that's just something more. Things will be 520 cm cubes, which is what we use to measure. So I think that would be probably best answer.